Problem 13 is giving us some reaction data and asking us to calculate the rate law. Let's start by writing out the generic form of the rate law for this reaction. The generic form is going to be rate equals K, the rate constant, NO2 to some exponent we don't know, times F2 raised to another exponent that we don't know. And our job is to figure out what the exponent X and Y are. To do that, we're going to look for two reactions. Let's start with focusing on X. So we're going to look for two reactions where the concentration of F2 is a constant. And so that means if I number these reactions over here, we're looking for two reactions where F2 concentration is the same. So it looks like we want to focus on these two initially. And there's a couple ways that we can approach this. So we could say, we can see when we double the concentration of NO2, so when we go from 0.1 to 0.2 and we've doubled it, what happens to the rate law? Or excuse me, what happens to the rate in that situation? It looks like the rate is also doubled. Let's confirm 0.51 divided by 0.051 divided by 0.026 is 2 when you round it to a sig fig. So since doubling the concentration of NO has the exact same doubling effect on the rate, that tells us that the exponent for X is 1. And then let's figure out what's going on with F2. And for F2, I'll solve in the other way, the mathematical way. So for F2, we're looking for two sets of data where NO has not changed. So that means we want to focus on these two data points right here. And the other method that we have for determining the exponent is to write the rate law with the information from the problem. So rate is going to be 0.051, and that is equal to our rate constant K times the NO2 concentration, 0.2 raised to the X, let's just keep pretending like we don't know what it is, times the F2 concentration, which is 0.1 raised to the Y. And we're going to divide all of that by the data for number 3. So in there, the rate is 0.103. That is equal to the rate constant K, the concentration of NO2, 0.2, again to the X, and the concentration of F2, 0.2 to the Y. And then we say K is a constant, it cancels, and 0.2 to the X divided by 0.2 to the X will also cancel. So here we are left with 0.05 divided by 0.103. That is 0.485, and that is equal to 0.1 divided by 0.2 to the Y. So that is 0.5 to the Y, and we need to solve for Y. You've got a couple options on solving for Y. You can just start plugging numbers in and see what you get, knowing that these exponents are typically 0 or 1 or 2. Or if you want, you can anti-log this thing so we can go all the way through the process of getting that X down. But I think that guessing and checking in this case, you don't even have to really guess and check. You can see that that exponent needs to be a 1. If Y was a 0, then 0.5 to the 0 equals 1. That doesn't work with our data. 0.5 to the 1 is 0.5, and that's pretty close to 0.485. 0.5 to the 2 is 0.25. That's pretty far off of our data, so that also doesn't work. Let's move on. Problem 14. The following reaction is known to be first order with a rate constant of that. If the reaction starts with an initial concentration, how long will it take? Blah, blah, blah. We've got the first order integrated rate law. So we have a rate constant, K. We have an initial NO concentration, so that is a 0. And how long will it take? That's what we're trying to figure out. That's our time. And we're trying to figure out how long it takes for the concentration to go to 0.01. So that's our A at time t. So what we're going to do is just plug in and solve for time. Natural log of 0.01 is equal to, don't ever forget that negative sign. It's very easy to forget, negative 0.0, what in the hell, 0.053 inverse seconds times the time, we don't know what that is, plus the natural log of 0.055. And now we just have to do algebra. The natural log of 0.01 minus the natural log of 0.055 divided by negative 0.053. Looks like our time is 32 seconds. What is the half-life of the reaction in problem 14? Giving us the half-life equation. T1 half is 0.693 over K. 0.693 over our value of K is 0.053. And so we just have to crunch the numbers on that. 13.1 seconds. The next problem asks us to find the graph that corresponds to the reaction in problem 14 and 15. This is one of these situations that confuses students a lot. When you're looking at the integrated rate law, remember there's 3 different forms for first order, second order, and zero order, and they all have slightly different terms. One of them is the natural log. One of them is, whoa, what kind of funkiness is, oh yeah, one of them is a natural log. One of them is 1 over something. And one of them is just the concentration of something. And for each one of these unique graphs, we will get a straight line when we've graphed the data correctly based on the type of the rate law. So we know that we're looking for a straight line, which means that that graph is not correct. And so we've got it narrowed down to the 2 natural log graphs. One of them has positive slope, one of them has a negative slope. How are we going to figure it out? Look at the equation that we're using. This is telling us negative K, which is telling us that the reaction, when it's plotted, is going to have a negative slope.